This movie deals with heat. It is intended for viewing before students do a laboratory experiment designed to illustrate the determination of specific heat by calorimetry. Upon completion of the laboratory activity associated with this movie, students will be expected to be able to define and relate temperature, heat, heat capacity, and specific heat, interpret algebraic signs of heat values, explain how specific heats of materials can be obtained by comparison with water, explain how a calorimeter is used to determine specific heats, and describe how specific heat can be used in the identification of a substance. Let's start with some definitions of terms that we frequently encounter when dealing with the subject of heat. The term system refers to any part of the universe that we are interested in. The term surrounding refers to anything else in the universe besides the system. Temperature can be loosely defined as the measure of the hotness of a system. Two systems are said to be at the same temperature if putting them in contact does not lead to either one getting hotter or colder. We know from experience that if we put a hot object in contact with a cold one, the hot object cools down and the cold object warms up until both are at the same temperature. Heat can be defined as something that flows from the hot object to the colder one. However, experiments by James Joule show that the same effect on the colder object can be done by doing mechanical work on it. Since doing work on a system results in a change in energy, the thing that is transferred when heat flows is in fact energy. A measurement is essentially a quantitative comparison. In the case of heat, which is often represented by lowercase q, the basis for comparison was historically based on the amount needed to raise the temperature of 1 gram of water by 1 degree Celsius. More specifically, from 14.5 degrees Celsius to 15.5 degrees Celsius. However, James Joule has shown that a mechanical paddle wheel stirring the water can achieve the same effect for mechanical work. The amount of work needed, which we know now, is 4.18 joules. The official abbreviations for calorie and joule are CAL and uppercase J. These days, we measure heat by using the fact that the amount of heat needed to cause a temperature change in a given system is proportional to the temperature change. In other words, Q, the amount of heat, is equal to some constant, written here as uppercase C, times delta T, the change in temperature. Simply stated, if you want to cause a bigger temperature change, you need to put more heat into a system. Note that this equation applies only if during the process of heating or cooling, no chemical reactions or phase changes are happening. Examples of phase changes are melting of a solid, freezing of a liquid, transformation of a solid from one crystal form to another, etc. Strictly speaking, the equation is also approximate because the constant C, which we call the heat capacity, does in fact depend on the temperature. But over a small enough temperature range, it is a very good approximation. The heat capacity, C, is a positive number. A simple mathematical manipulation tells us that the heat capacity is equal to Q divided by delta T. Therefore, the unit for heat capacity is an energy unit divided by a temperature unit, joules per degree Celsius, or joules per Kelvin. Note that these units are identical because a 1 degree change on the Celsius scale is equivalent to a change of 1 Kelvin. Heat capacity depends on what the system is, as we shall see later. For now, based on the mathematical definition we have for heat capacity, let's see if we can define it in words. If delta T is 1 degree Celsius, it's easy to see that Q is equal to C. In other words, we can say that the heat capacity, C, is the energy needed to increase the temperature of a system by 1 degree. It is convenient to use algebraic signs in referring to heat flow. If heat flows into or out of the system, assuming no chemical or phase change occurs, Q is equal to heat capacity, which by definition is a positive number, times the change in temperature, delta T. By definition, delta T is T final minus T initial. Therefore, delta T is positive if the temperature of the system increases. T final will be larger than T initial. Conversely, delta T is negative if the temperature decreases. What happens if heat flows into the system? We know the temperature will increase. Therefore, delta T is positive and we expect Q to be also positive. In other words, a positive value of Q implies a flow of energy into the system. We could say that heat is absorbed by the system if Q is positive. Conversely, heat flow out of the system implies a temperature drop. Delta T is negative and Q is negative. In other words, we say that Q is negative when heat is released from the system. Let's apply these ideas to a pot of water on a hot stove. What is the algebraic sign of Q? We know heat will flow from the hot stove into the pot of water. Therefore, Q is negative for the hot stove and it is positive for the pot of water. So why is it convenient to assign algebraic signs to heat values? The reason is that we do heat measurements inside a thermally insulated system. By thermally insulated, we mean that heat does not flow in or out of a system, but heat can flow from one part of the system to another. For those parts where heat flows out, Q is negative. For those where heat flows in, Q is positive. Overall, Q would be 0. Remember that energy is only transferred. It is neither created nor destroyed. Consider a system with a heat capacity of 25 joules per Kelvin. Calculate Q if its temperature drops from 20 degrees to 16 degrees Celsius. Assuming no chemical or phase change, we use the equation Q equals C times delta T. Delta T equals the final temperature, 16 degrees, minus the initial temperature, 20 degrees. Therefore, delta T is negative 4 degrees Celsius, or negative 4 Kelvin. Therefore, Q is equal to the heat capacity, 25 joules per Kelvin, times delta T, negative 4 Kelvin, which gives negative 100 joules. The negative value of Q means heat flowed out of the system. The heat capacity of a system is defined to be the heat needed to raise its temperature by 1 degree. Common sense tells us that the heat capacity should depend on mass and what the system is made of. For example, which requires more heat, assuming the same temperature change? 1 gram of water or 2 grams of water? Obviously, it takes more heat to raise the temperature of 2 grams by the same amount. Therefore, we can say that the heat capacity, C, is directly proportional to the mass of the system. Mathematically, we can write that C is equal to some constant, shown here as lowercase s, times the mass of the system, shown here as m. The proportionality constant is called the specific heat. A simple mathematical manipulation allows us to write S as C divided by m. In other words, we can define specific heat as heat capacity per gram. In all of these, we are assuming that the system is homogeneous, that is, uniform throughout. This is generally true of samples of pure substances. The formula Q equals C times delta T is more convenient to use when dealing with a non-homogeneous system. If we're dealing with a homogeneous system, it may be more convenient to use the formula Q equals S times M times delta T. Specific heat depends on the composition of the system. Water, for example, has a specific heat of 1 calorie per Kelvin per gram, or 4.18 joule per Kelvin per gram. Copper, on the other hand, has a much smaller specific heat of 0.39 joules per Kelvin per gram. Because water has an unusually high specific heat, it takes more heat to change its temperature. This is the reason why it's the best coolant, apart from the fact that it's also cheap and abundant. The unusually high specific heat of water is also the reason abrupt, drastic changes in temperature are less likely to happen in places next to large bodies of water. Let's look at a simple example to clarify the distinction between specific heat and heat capacity. Suppose it takes 836 joules to raise the temperature of 100 grams of a liquid from 15 to 17 degrees Celsius. What is the heat capacity of the sample? What is the specific heat? The heat capacity is the amount of heat flow, Q, divided by the temperature change, delta T. From the question, we see that Q is positive 836 joules. It's positive because we know it has to be absorbed if the temperature increases. Delta T is the final temperature, 17 degrees, minus the initial temperature, 15 degrees Celsius. That is, delta T equals 2 degrees Celsius. Dividing 836 joules by 2 degrees gives us 418 joules per degree Celsius, or 418 joules per Kelvin as the heat capacity. The specific heat is the heat capacity per gram. It's equal to C divided by M. We have just found C to be 418 joules per degree. The mass is given in the question as 100 grams. Dividing 418 joules per degree by 100 grams gives us 4.18 joules per degree per gram. What liquid do you think this is? It's probably water. A calorimeter is a thermally insulated apparatus used for heat measurements. Heat measurement is also known as calorimetry. A key idea that you need to know in order to understand how heat is measured in a calorimeter is that inside the calorimeter, Q equals 0. Energy is neither created nor destroyed, merely transferred from one system to another. Because we have adopted a convention of assigning algebraic signs to heat flow, the net flow of the heat within the thermally insulated system must be 0. The phrase calorimeter constant is frequently used in calorimetry. It is simply the heat capacity of the immediate surroundings of the system being studied. That is, the container, the thermometer, the stir, the air. Note that we're dealing with something that is not homogeneous. It's more convenient to lump all of these parts of the immediate surroundings as one, and assign one value for the heat capacity, rather than try to deal with the specific heats for each individual part. Here's an example illustrating how the calorimeter constant of a calorimeter is determined. Imagine a 70-gram sample of a metal with a specific heat of 0.3 joules per Kelvin per gram at 100 degrees Celsius. We pour this sample into a calorimeter containing 100 grams of water at room temperature, which is 20 degrees. What do we expect to happen? We expect the final temperature to be between 20 and 100 degrees Celsius. Let's say it's 23 degrees. Heat would flow out of the metal, which is hotter. Q for the metal equals mass of the metal, 70 grams, times specific heat of the metal, 0.3 joules per Kelvin per gram, times the temperature change for the metal, 23 degrees minus 100 degrees, which is negative 77 degrees. This gives us a Q value of negative 1,617 joules for the metal. As expected, Q is negative because heat flows out of the metal. Heat would flow into the water. Q for the water equals mass of the water, 100 grams, times specific heat of the water, 4.18 joules per Kelvin per gram, times delta T for the water, 23 degrees minus 20 degrees is positive 3 degrees. This gives us a Q of positive 1,254 joules for the water. Note that of the 1,617 joules lost by the metal, only 1,254 joules went to the water. Where did the rest of the heat go? Heat would also flow into the immediate surroundings of the water, that is, the rest of the calorimeter, which is initially at the same temperature as the water. We refer to the heat flow to the rest of the calorimeter as Q-cal. Since the calorimeter is insulated, total Q is equal to 0. In other words, Q water plus Q metal plus Q cal equals 0. We know Q water and Q metal. It should be easy to solve for Q cal. we get a value of positive 363 joules. Note that the positive Q values, 1,254 and 363, add up to 1,617, which is the absolute value of the negative Q value. Now that we have Qcal, we simply divide it by delta T to get the calorimeter constant. Delta T for the rest of the calorimeter is the same as the delta T for the water. Only the metal was hot to begin with. Water and the rest of the calorimeter were originally at the same temperature. Note that we have been keeping more significant figures in these calculations than we are supposed to according to the rules. For a series of calculations, it is customary to keep an extra digit in the intermediate steps in order to avoid building up round-off errors and overestimating the uncertainty in the final answer. The calorimeter constant given here should be rounded off to only two significant figures, if that is the main goal. In practice, however, the calorimeter constant is meant to be carried over to another calculation. To determine the specific heat of an unknown metal, we simply mix it with a known amount of water and a calorimeter with a known calorimeter constant. Consider the following example. Suppose a 150 gram sample of metal at 100 degrees Celsius was poured into a calorimeter containing 100 grams of water at room temperature, 20 degrees Celsius. If the final temperature of the mixing is found to be 24.5 degrees Celsius, what is the specific heat of the metal? Assuming that the calorimeter constant is 125 joules per Kelvin. The temperature of the water went up by 4.5 degrees Celsius, so Q for the water must be positive. Q for the water is equal to the mass of water, 100 grams, times the specific heat of water, 4.18 joules per degree, times the change in the temperature. Delta T is 4.5 degrees. This gives us a Q of a positive 1,881 joules for the water. For the rest of the calorimeter, Q is equal to the calorimeter constant, which is given as 125 joules per degree, times delta T, which is 4.5 degrees Celsius. Qcal in this case is equal to positive 562 joules. Again, since the total Q inside the calorimeter must be equal to 0, we can solve for the remaining Q, which is that for the metal. Q for the metal is negative 2,443 joules. Since Q metal is equal to the mass of the metal times specific heat of the metal times delta T for the metal, we can solve for the specific heat of the metal by taking Q of the metal, negative 2,443 joules, and dividing it by the mass, 150 grams, and the temperature change. The temperature of the metal dropped from 100 to 24.5. Delta T is equal to negative 74.5 degrees Celsius. This gives us a specific heat of 0.219 joules per degree per gram.
The law of Dulong and Petit states that the molar heat capacity of an element, written here as C sub m, under ordinary conditions is approximately equal to 3 times R, where R is 8.314 joules per Kelvin per mole. This is the same R in the ideal gas law. The molar heat capacity is related to the specific heat by the following equation. Molar heat capacity, C sub m, equals specific heat, S, times the molar mass. The molar mass of an element refers to the mass of 1 mole of atoms of that element. A mole of atoms is a collection of 602 billion trillion atoms, that is 6.02 times 10 to the 23rd atoms. Numerically, the molar mass in grams is equal to the atomic mass shown on the periodic table. For example, copper has a molar mass of 63.646 grams per mole. If we multiply this by S, the specific heat, the law of Dulong and Petit says that the result is approximately equal to 3 times R. Thus, we can solve for S and estimate that for copper it is approximately 0.39 joules per Kelvin per gram. An obvious application of this law is the identification of an unknown element by experimental determination of its specific heat. The molar mass of the element will be equal to the molar heat capacity, C sub m, which is approximately equal to 3 times R, divided by the specific heat S. Then, we can simply look at a periodic table and find the element with the closest molar mass.
Here's an overview of the experiment you will do. First, you will do a standardization run. The purpose of the standardization run is to determine the calorimeter constant. You will mix the metal with a known specific heat, in this case copper, with water. You will heat 200 to 300 grams of copper and mix with 100 grams of water. Be sure to record the precise masses. You will measure the temperature of the copper shots in water before mixing and after mixing. Then you will do an unknown run. The procedure is essentially the same, except that you will use the unknown metal shots. The goal of the unknown run is to determine the specific heat of the unknown. You will need to use the calorimeter constant from the standardization run in your calculations for the unknown run. Here are some pictures in the movie demonstrating the procedure. You will put the metal shot in the dipper. Put the dipper with the metal shot in a boiler to heat it. Once the temperature is close to 100 degrees, pour the metal shot into the calorimeter, in which you should already have 100 grams of water. You should be recording the temperature of the shot and the water just before mixing, and a few minutes after mixing when the temperature stabilizes to its final value. Here's how to analyze your data. For the standard run, you need to look up the specific heat of copper. Refer to the CRC Handbook of Chemistry and Physics. From your experimental data, calculate Q water and Q copper using the equation Q equals mass times specific heat times delta T. Note that the specific heat of water is 4.18 joules per Kelvin per gram. Delta T should be positive for water. Its temperature will have gone up. Delta T should be negative for the copper. Note that the total Q inside the calorimeter should be 0. Calculate Q for the calorimeter, QCal. QCal should be positive. Then calculate the calorimeter constant, CCal, by taking QCal and dividing it by delta T for the rest of the calorimeter. Delta T for the rest of the calorimeter is the same as for the water. For the unknown run, calculate Q water. Then calculate QCal using the calorimeter constant you obtained from the standard run. Delta T for the calculation of Q water and QCal should be the same. Once again, knowing that the total Q inside the calorimeter is 0, calculate Q for the unknown metal, which should be negative since it cooled down. Finally, calculate the specific heat of the unknown metal by taking Q of the unknown, then dividing it by the mass of the unknown and delta T for the unknown. Delta T for the unknown should be negative. Its temperature decreased. Once you have calculated the specific heat of the unknown, estimate its molar mass. Identify your unknown based on the list of possibilities provided by your instructor. You will need to refer to the CRC Handbook of Chemistry and Physics to look up the specific heats and molar masses of the list of possible unknowns.